Welcome to Weld.com. We have Mr. Garrett Vickery, our NDT instructor, non-destructive testing. Welcome back. I believe we've done some sessions with you on dye penetrant that were very interesting.
We did have a good time.
It was a good time. I swore up and down we had something that was going to have an indication, and you didn't find it. It was some kind of weird grain structure on titanium, and I thought, man, we're going to find all kinds of goodies in that, and there was nothing there. It was just grain structure. So you brought another piece of equipment down, another process. Tell me, how many processes of non-destructive testing do you have in your program? What do we do besides the obvious, the dye penetrant, the visual, X-ray, and that kind of stuff? What else do you have?
We teach the traditional 5 methods, right? The penetrant, like you mentioned, magnetic particle, radiography, ultrasound, which we're about to get into today, and eddy current.
Eddy current. What's eddy current?
Oh man, it's an interesting process where we utilize passing current through some coils to create magnetic fields, scan them on a conductive material.
I've had a lot of my students come through my program, and then they go through your program, which is a good move, by the way. But for why is it that these people that I pass them in the hallway or we're talking, they grumble? They're all like, eddy current, man. I'll ask them, hey, how's things going today? You know, and they go, eddy current, I hate it. You know, what's going on with eddy current that nobody likes?
It's got some complicated theory behind it. Why the things that happen on the screen are a little elusive. Just take some time to play with. But once you wrap your head around how the magnetic fields and the currents communicate with one another, then it's smooth sailing, but it takes a while to get that acclimation.
So what are you reading? What are you detecting? Visual things on the surface, subsurface? What are we looking at?
It is slightly subsurface, and I want to be specific in saying that because we can get some thicknesses of materials, but we're very limited with eddy current. But we are detecting conductivity changes and or looking for flaws or irregularities, mainly towards the surface of the material.
Okay, which leads us into ultrasonics? Ultrasound. So we're able to look inside this part with ultrasound?
All the way through, no limitation. It's a volumetric inspection, meaning I can interrogate all the way through.
Really?
Yes, sir.
Okay, you have a part down here that is made by Flawtech, so I'm assuming this is some kind of a standard. I mean, it's got known flaws in it. We don't know it. I don't know it.
Correct.
But you can find them, huh?
Yes, sir.
Because I'm going to visually look at this, and other than some POC and some whatever, the root looks a little cold. But, you know, visually we glance at this and we think, well, that's all right. What's wrong with it? I'm looking at the profile. I don't see anything on the edge. I'm looking at this profile. I don't see anything. We got a nice little nugget cut down through there. And I don't notice, there's a little bit of undercut on this top toe up here, but I don't see anything major as far as just looking at this.
It is deceptively clean looking.
Okay. I like that word, deceptively. Because I don't, you know, we've gotten into some good arguments, and we'll bring another piece out here in a little bit that, you know, you glance at stuff visually and you take for granted that, hey, it's there, it's good. So what are we going to do here to scrutinize this piece? What are we going to do here?
Well, what I've already done is I calibrated my instrument here. This is a GE USN 60. It's a typical flaw detector. It's multi-purpose, does a lot of things for us. But I use this IIW block here, and the interesting thing about ultrasound is I have to know some things before I go and try and tell you things about what I don't know. For example, I calibrated distance using this radius because it's a 4-inch radius, so that when I can tell you how far away from my transducer that flaw really is.
This being a transducer?
This being a transducer, yes, sir. And we also have a 60 thousandths hole that I set my sensitivity to, meaning how high my signals jump up here on this screen is all comparative to this 60 thousandths hole that I'd calibrated on. So then I can give you size estimates.
Oh, okay.
Pretty accurately.
So, I've been out in the field and out in the refinery, and I've been asked to do certain things on a certain place, and I'll get a grease spot, I'll get a UT shot of a wall thickness of a piece of pipe that's been in the refinery for a long time. I want to know how thick it is before I put a weld of lead on it, and we're going to bore through and do a valve or something. how do they calibrate in the field? Same way? Do they have something
process.
that they're using to?
So what we're getting into today is called shear wave. We're sending sound at an angle, at a known angle through that material, and what you're referencing is thickness measurements where they want straight down and straight back, and they're timing how long that sound goes to the bottom of the material, and if obviously there's less material, sound comes back sooner, and that's represented on the chain.
So like in my instance, I've got a piece of 10-inch Schedule 40 pipe. We know what the wall thickness of that when it was put in. We can go look that up.
Yes, sir.
But then they're getting a reading that says that it's 0.128. Now we know that there's internal corrosion, POC, whatever, on the inside of that, and then we're no longer our true wall thickness anymore.
And then under pressure, and if you got some crude flowing through there, it's not the cleanest. We've got some sand in there, it'll erode away very quick.
I've been around some areas where I'm reading those UT, I look by, I'm going, gets a little, because you know what's flowing through there under high pressure, like you said. Okay, so how do we go about this here? We've got a known thickness.
We do.
And we've got our weld sample here, and you're going to be looking at this weld joint.
So up here is the transducer. So this has a piezoelectric element in here that's going to take these electric pulses and convert them to mechanical energy. And send that mechanical energy through the material. That energy is going to come back at some amount and vibrate this again, and it's going to convert that back to electrical and give us a signal. So I'm sending that sound through this material at a 70-degree angle. It's going to skip off the bottom, come back to the top, back and all the way through.
Cool.
It's very interesting, and just like, if we were at the doctor.
What do you have here?
We're going to put the jelly on the belly, Bob.
Jelly on the belly.
Yes, sir.
Sound safe. This is Sonotech, same stuff you do ultrasound on a, really, at the doctor's office, kind of?
Yeah.
Okay, so this is like a medium that you can slip and slide and make continuity with the part and the transducer?
Yes, sir. Because ultrasound does not travel through air very well. So
what do you do? Just put a blob on the material?
Yes, sir.
You don't need to get real dainty with it either, huh?
Yeah.
Kind of like that?
Yeah, that's
I'm good at this already. Yeah. I can nickname that welder's jelly right there,
yes,
huh?
Sir. So when I come down on this material, I want to spread this out nice and thin because I don't want any air under the transducer. I want a good couplant. Well, this is technically termed couplant.
All right.
So when I come down here, you'll notice that my screen is set to a 10-inch range, meaning that touching the transducer, see if I touch this with my thumb, I get some sound reflection from my thumb.
Okay.
Right? So this is touching the transducer to all the way down the screen representing 10 inches of material travel.
Travel this way, linear this way.
Whichever way I aim her.
Okay. So
when I set down here, you'll notice that I have a very large blip here at about 7 inches away, which, if we wanted to measure that, absolutely.
It's leaving the end of the material.
It goes all the way down.
Okay.
And so what I'm interested in is everything in between, specifically about halfway, which is this guy right here.
Okay.
That's going to be our weld signal. And if that weld signal stays there throughout this whole scan, my life is good. However, if it breaks this plane, this 50% screen height here.
Here?
Yeah.
This being height?
Here. Yep.
Okay.
Yep. Now that's what I calibrated that 60 thousandths hole there I mentioned to.
Okay.
To tell me that anything that comes up to here, 100%, is 60 thousandths. So if it comes up halfway, half of 60 thousandths.
Okay.
Right? So anything that size, we definitely want to interrogate. So I'm going to scan around, called raster scan. You notice I had a little blip right there, nothing too bad. I'm going to raster scan, we call this. I want to overlap at least halfway each pass and boom.
Oh, boom.
We've got...
we just pegged off the screen here.
Yeah. So we have something there that is returning sound at a great amplitude, meaning it's sending back a lot of sound, and so that shows as the signal height. So this direction, signal amplitude or size of flaw. In this direction, distance from the transducer. So that's pretty close. We're about an inch, 1.5 inches away.
Which is right here in the weld.
Yes, sir. We can actually measure that out. So I've got, see this little green gate here. Some of you might have been wondering what's going on with that green gate.
This one here, up about
This gate right here is
Okay.
giving me this numbers information up here. Now we do, a lot of folks don't think us industrial folks know how to count some numbers and do some math, but we can triangulate where this flaw is by using sine, cosine, and tangent.
Okay.
Right? Or I can set this gate and let the computer do it for me. You know, this is 2018, right?
Okay.
So right now this is telling me 1.4 inches from my beam exit point out is where that flaw is.
Where's the reference to your beam exit point on here?
There is a little laser etched line right on that transducer that's going to
This
tell
guy
us.
right here?
Yes, sir.
So at the very bottom or up at the top?
So that's the travel from the transducer out to the end of the face.
Okay.
So where that line is where I'm going to take my measurement from. And then I can tell you exactly where that flaw is. So there's no guesswork on where you need to get friendly with your grinder.
Cool.
So let me come back down and try and find that again. Raster scanning, bingo. And judging by the shape of that signal, we can tell that that's something that's very sharp, very crisp, such as
Sharp as in you can determine what type of inclusion or discontinuity
Yes, sir.
or defect it is.
yes, judging by the way that the sound returns. Because picture you take a pebble, you throw it in a pond, and it causes a ripple out.
Okay.
Right, and there's a tree in the way. And it's going to send back that ripple back towards the initiating source.
Okay.
And so depending on whether that tree is irregularly shaped, wide, round, has a lot of peak points on it, or whether it's just nice like a crack versus an irregular slag inclusion that's all weird shaped.
Okay.
So 1 point, now it's saying 275. So I'm going to pull this out to 1.275. 1.275. And I'm going to measure from that point out. Boom. And that's right there in the middle. Take me a little pencil, mark that right there so the welder knows right where to go grind. And I can even tell you. Ooh, that's much better. And I can even tell you this DA right here is going to tell me that that flaw is 0.29 inches down into the material. Now we got a 3/8 plate here.
Not necessarily from the top crown of the weld,
Top
from the
down.
material thickness down.
Top down.
From top of weld or top
Top
of
of
plate?
weld,
Oh,
yeah.
top of
Top of
weld
weld.
down,
Yes, sir.
0.29. So we're about middle of the weld actually. We're about halfway through the material in the weld nugget.
It's on the lower portion because this is a
Right.
375 plate. So-
Interesting.
Yes, sir.
So you can really look around and do some things.
Oh yeah.
That's fascinating. I have a piece here. I think I made this for you guys quite a while back. I know, no, it wasn't too awful long a while back because I know I welded it with one of the ESOB Rebels. And this is no fault of the machine. This is every fault of me and technique. But if I have you look at this, and I think this stemmed from a conversation that I was having with an NDT student about visual and looking at things. I mean, we look at this and you glance at that and you think, well, that's pretty good looking weld. I mean, it's in there. It's obviously a coupon cut. It's got 3 passes visually, which indicates to me that we did this in the horizontal with short arc MIG. The root pass looks like it's in there,
It does.
right?
Yeah, that's good looking.
Visually, yeah. But I've also had some welds that look just like this. We've sanded them down, cut the coupon, prepared the coupon and put it in the bend machine. This is back when we had the old one. Took about 3 cranks on the old hydraulic press and I mean it just snapped. I mean it splintered.
Yeah.
And here's why. Because I was lazy enough, again, no fault of any machine. We're running the machine correctly, obviously. Right wire, right voltage, right wire feed speed and all that stuff. I was lazy enough that I didn't clean in between passes. In the horizontal weld, you really need to get that deposit, that glass, that silicon deposit stuff out of there because short circuit MIG doesn't have any kind of real arc force that it's going to dig and
blow it out, yeah.
right, not like stick, 60-10, stuff like that. So I just got completely lazy. Now look at this coupon. What do you see?
Oh, yeah, there's a little.
Yeah, it's like, hello.
Yeah.
And you don't need the dye pen, but we could really make this thing light up. We've got multiple holes over here, and that looks like a nice little line there of lack of fusion. In any event, stick your probe on here and see what we got. Just out of curiosity.
And we reduce, reuse, and recycle here, so I'll just scoop some of this up onto here and transfer it right over. All right, so I'm just coming down on here, and we already got something. See what I mean by that signal? See how this is 1, 2, 3 peaks? It's irregularly shaped, so it's sending sound back in an irregular manner.
So it's not necessarily porosity.
It's not, yeah.
This would indicate the stuff that I left behind, which were those
nasty
linear deposits of slag and glass. I think I've got a good reference to that here. I'll find it in the shop. We'll get some B-roll of that slag that we're talking about, the glass brown deposits that commonly left behind by gas metal arc welding. Man, this thing's like loaded with stuff.
Jeez, yeah.
I mean, we're really active right here in all kinds of signals.
Oh yeah. Well, and remember, like before, we have this back wall signal, so we want that to stay relatively put. Touching the transducer here, and then we're interrogating the weld with that signal there. And that's just, there's multiple points. I mean, at least 3 or 4 that I've counted already that jump over our interrogation limit. So there's a form that I'd go through, and this gain setting up here is like volume on your radio. How loud am I listening to that music?
Right.
And I compare that to the gain it took for this signal over here, and comparative analysis, put it through a couple of equations, and we can determine acceptance and rejectance. But from the look at this, with as many
You're just
as
dying
there
to
are,
reject my weld, aren't you?
I mean, you know,
Huh?
when
Go
Bob
ahead and say
Moffat
it.
hands you a weld, you don't expect this. So
Well, I'm getting better. You know, I'm trying.
yeah.
Wow, that's I do remember making this because I wanted to get to that point of visual versus, man, you better look at that. Better not. You don't trust anything.
Right.
That's the reason we have NDT.
Sir.
You know, we can walk by a weld that, pipe weld or something, and you'd say, wow, somebody's a good hand there. Doesn't have any root in it. How do you know what's in the inside of anything? So, question everything. Don't trust anything. Been my philosophy over the years. But
well, and with the way that this is aligned, it's more like a linear inclusion. So it's in a line, right? So if that's just a shear point waiting to happen. I mean, really, any pressure or stress that weld's put under, it's not going to last.
you know what we're talking about when we say that glass, that brown.
Like a silica?
Yeah, hang on just a second. I'll be right back. This is typical. Decent looking weld, but it's all these spots, these random spots, and they're like I kind of want to call them a glass.
Yeah.
Because I can get a scribe or something sharp, and I can actually, you can tell how some of them have been. When the weld cools off, they flick off. But that's just normal. That's the end product of deoxidizers in the weld.
Yeah.
Well, when we're making a multiple pass groove weld, where are those going to line up? They're going to line up on the toe of the weld. So, I like to reach in with a die grinder or a real thin bladed grinder and a wire wheel and clean those out every time I make a weld. I didn't do it on this one. I didn't do it purposely so that we could show what happens. Anyway. That's what those look like. Garrett, that's some interesting stuff.
Yes, sir.
You didn't need to dog me out that hard. I mean, no, that was interesting to be able to look inside a part with sound waves and you know what you're talking about when you're talking about the size and shape by looking at the screen. Good operator, somebody out of NDT, do all 5 methods pretty sharp. What are we talking about starting out? You graduated from Cali, did you not?
I did, yes, sir.
And then you did an internship, or you were already working, or you went and did an internship?
Yeah, I went and interned there at Wolf Creek. It's the nuclear power plant here in Kansas, and
Flint Hills.
Yeah.
Okay.
And I started out $1,000 a week.
Stop it. $1,000 a week.
I'm not lying to you.
Wow.
Yeah, and that's entry high. I'm fresh out of college, and we're certification based, kind of like welding. You got to prove yourself, get out there and get some experience and go before a board and take a test. So with that certification comes even more bargaining power on what you can make.
Nice.
And it's also very industry dependent. You got some welders out on a pipeline making a doctor's wage, and right behind them, we're taking radiography at every weld they lay down. So, we're in it with you.
So is there anything beyond this? I mean, is this kind of like it? We're talking ultrasound and shear wave.
Yeah.
What's next beyond this?
Oh my, no, this is...
What do you got?
This is traditional, we'll call it, right? And then now we got the new age. And so what's up next for ultrasound is we're doing phased array. And so phased, picture timing.
Okay.
And array, picture this is one sound crystal sending one sound beam at one angle. So we can line up with phased array multiple sound crystals, and we can fire those elements at different times to steer and focus that wavefront so that we can interrogate this at a lot higher scrutiny. And not only that, this is just interpreting blips and signals, right? To me, I know what this means, but if you hand this to somebody who you're telling them their $500,000 components no longer usable, phased array, we can develop an image that gives you like almost a geographical representation of where that flaw is, how big it is, and so it just makes a lot more sense.
And depth and everything else?
Yes, sir.
You can produce an image off of this information, except so
rather than
phased array is like ultrasound on roids. Is that what you're telling me?
That's
really?
The way to say it. Yes,
is this new technology just by computers, or what is this?
Yes, with the think about how far your phone's come in the last 10 years, Bob. We ain't flip phoning no more. So right about, we'll say 2012 is really when phased array got its big kick from Olympus, and a couple other companies jumped in.
Tell me where this might be used. I mean, what?
Oh boy, so aircraft uses it a lot to interrogate their composite skins, refineries.
So I've seen the composite skins. I've been through Boeing years ago. We did some stuff, and I'm watching these composite engine cowlings and stuff, and they're just shooting a beam of water at it from like 10 feet, and it's just going continuous for 8 hours.
And
they're reading.
Did it have two going along the whole?
Yep.
Yeah.
It did.
So that's.
But now they're using phased array to. Where else? What are we looking at? What types of welds?
On a pipeline, instead of you seen me having to go back and forth like this, with the phased array, I can mount it up in a scanner and just go all the way around that weld one time, and I've got a laid out strip chart of all of the information inside of that weld.
Wow.
Yeah, man.
That's quick.
It's heavy.
That's quick. We have like, I don't know how many hundreds of wind towers around here. And that's some pretty heavy stuff. That's some thick steel, lot of big heavy fillet welds at the base, the seam welds.
I just spoke with the company here. We had a conference call between this company and our students here. They're wanting to hire some technicians, and they were explaining about who they are and what they do. And they make 300-foot sections that contain each section about 500 foot of weld, and every inch of that weld is interrogated with shear wave ultrasonics.
Unreal. How long does that take? Give me a timeline on that inspection process.
Oh, we probably go about inch or two a minute. You really want to take your time.
Right. On the components like that, yeah. Interesting. That's fascinating stuff. We appreciate your time and your knowledge on all this. I'm not, I haven't been around the internals and had this really explained to me. I'm very interested, especially when I know I can make a jacked up weld like that, and then you can find everything. I got to get better, huh?
Practice, Bob.
It's all about practice. We're always talking about practicing and getting better. For us, I think it's more like, and it's extremely beneficial to have your program right here next to ours, because, at times we can teach this backwards. We can take something like this and say, yeah, you might think that's good, but it isn't. So we kind of like teach it backwards. We got flaws. How do we avoid those flaws? Right. Is it by settings? Is it by technique? Or do you just need to learn how to clean them between each pass? So really appreciate your time, Garrett. That's good stuff. Good stuff. Man, I hope this helps and it was entertaining and educational. It sure was for me. Thanks for watching Weld.com. Bob Moffett and Garrett Victory with Cali College. Thank you.